This is lesson 4, part 1, finding limits by analytic methods. So topic 1.6, we're going to be determining limits using algebraic manipulation. Sometimes the graph can be misleading, and sometimes it might not be practical at the moment to find the graph. So we're going to look at how you can do it algebraically. We've kind of been skirting around this issue the last 2 topics. So we're going to use our limit properties from before, but now we're going to use them algebraically. We're also going to look at a couple of limit theorems, and we're going to end the lesson by talking about the squeeze theorem, which will follow to come. We'll see how that works out as we go. Okay, so the methods we have to try are listed here. We have direct substitution. We have the principal limit theorem, factor cancellation technique, and a lot of these, once you do something like factor, cancel, you go back to step 1. So the idea is hopefully we can get back to a point where we can substitute. The next one is the conjugate method, and you want to rationalize. A lot of times it is the numerator, sometimes it's the denominator. Once you rationalize it, what you'll find is you can go back to step 2 and use the principal limit theorem. So we'll get to that, what that is, in just a minute. Next one is called the special trig limits, and these are the 2 where the squeeze theorem comes in. These are 2 you'll have to memorize. The limit as x approaches 0 of sine x over x is 1, and the limit as x approaches 0 of 1 minus cosine x over x equals 0. Now, they might seem kind of unusual, but believe it or not, they are ratios that come up often, and their limits are used quite a bit. So we'll be talking about those at the end of this section. And this is where these 2 are where the squeeze theorem comes in. And that's how we end the lesson, with the squeeze theorem. Okay, and then finally the last rule is L'Hopital's rule. And as you can see, this will be presented in Unit 3 because we need a few more techniques of calculus before we can use L'Hopital's rule. Okay, so our substitution theorem is one of our limit theorems. So it's pretty straightforward. It says if f is a polynomial function or a rational function, then the limit of the function as x approaches c is going to equal the value of the function at c. The value of the function at c. Provided that if f is a rational value, the value of the denominator does not equal 0. Because of course, the limit has to exist. It has to be a real number. So if the denominator is 0 when you substitute, then you're going to have an undefined function and you won't have a real value. Big note here, always try to substitute first. It's the quickest way, it's the easiest way. Sometimes you do a lot of work and you don't even need to. But if you get a fraction like 0 over 0 or infinity over infinity, which are both undefined fractions, you should try to simplify the expression using one of our other algebraic techniques and then go back and substitute again. So let's do example 1, which says find each of the following limits analytically using direct substitution. So these are pretty straightforward. So we're going to take the limit of the polynomial 3x squared minus 5x plus 4 by direct substitution. So we can substitute 2 in for x and then find the value of the limit that way. So doing that, I'm going to get 12 minus 10 plus 4. So my limit is 6. Letter B, same thing. We're going to substitute 2 in because we're finding the limit as x approaches 2 of the rational function. So we're going to have 2 to the 3rd plus 1 over 2 plus 1. And since we have addition in the denominator, we don't have to worry about this rational function equaling 0 at 2. So we're going to have 9 over 3. So our limit is going to be 3. Next one, we're going to take the limit as x approaches e of ln of x over 3x. Again, we're going to do direct substitution. So we're going to take ln of e over 3 times e. Hopefully you remember your properties of ln and logs, and ln of e is 1, and we have 3e in the denominator, so that's going to be our value. Next, we're going to take the limit as x approaches 4 of the cube root of x plus 4. So we're going to substitute, and we're going to have the cube root of 4 plus 4. So this is going to give us the cube root of 8, which is equal to 2. Okay, a couple more. You can even use direct substitution with sine and cosine, our trig functions. So we're taking the limit as x approaches, theta approaches pi over 6 of sine of 2x. So using direct substitution, we're going to get sine of 2 times pi over 6, which is going to equal sine of pi over 3. And of course, from our unit circle, this equals square root of 3 over 2. And then finally, we're doing log base 3 of x plus 4, and we're going to do direct substitution. We are going to have log base 3 of 5 plus 4, because we want to find the limit as x approaches 5. So we're going to have log base 3 of 9, and that is, of course, the value 2. So that's how direct substitution works. Okay, next part is looking at discontinuities. And of course, we have 2 types of discontinuities, and we're going to list some strategies here that we can use. So the first thing we always want to try with this is first to factor both the numerator and denominator. And the reason we do that is to simplify the fraction. Because when we do that, it could lead us to one type of discontinuity, which is called a point discontinuity, or as we talked about last year, a removable discontinuity. So if we've been able to simplify, we are going to have a point of discontinuity where we have a hole in a graph. Occurs when factors are removed or canceled, however you want to say it. And of course, this happens when x minus a equals 0. And then finally, our other type of discontinuity is the non-removable one. So this is when we have a non-removable discontinuity. We have, of course, an asymptote. So this occurs when factors don't cancel. And so we're left with the situation x minus a is going to equal 0. And that's a bad thing because we're going to have a break in the graph. Okay, so how do we work with these? So you can perform the same algebraic analysis to find the limits of the removable ones, or point discontinuities, and we are going to be using the factoring method or the cancellation technique to deal with those types. The other type, they're a little more tricky and they take a little more subtle work. So let's go through using the factoring method or the cancellation technique. So using the limit as x approaches 2 of x squared plus x minus 6 divided by x squared minus 6x plus 8, you should always start. Now, I've already told you where you're going to use the cancellation method, but if you don't know that, you should always start from the point that you're going to do direct substitution. So I'm going to over here in the corner, I'm going to do that. So if I directly substitute 2 in, I would get 4 plus 2 minus 6 over 4 minus 12 plus 8. And what you're going to see is we end up with 0 over 0. So you might not have noticed that when you started the problem, if you just have some limits you have to take. So that's why you should always start with direct substitution. And of course, this is bad because it's not defined. So we are going to go back and factor our two polynomials and hope that we have cancellation of factors. The numerator factors into x plus 3 times x minus 2, and the denominator factors into x minus 2 times x minus 4. And we can see that the x minus 2's cancel, so our limit becomes this simplified rational function. So we're taking the limit as x approaches 2 of x plus 3 over x minus 4. Now at this point, you should always try direct substitution again. And when we do that, we now have 2 plus 3 over 2 minus 4. So we get 5 over negative 2. So what that tells us is that the limit as x approaches 2 of x squared plus x minus 6 divided by x squared minus 6x plus 8 is going to equal negative 5 over 2. So that's how you use the cancellation or factoring technique. Okay, so let's put this all together a little bit. So looking at a graph of a function, we can see that just because it's undefined at a specific x value doesn't mean we can't find the limit. And we talked about this in lesson 2. And I'm recalling you to the Hoover Dam construction picture where you had the bridge almost done and it wasn't quite connected, but you knew where it was going. So we have the same kind of look here where we have this hole that I'm talking about, which is right here. So even though the function is not defined there, if we look at the limit from the left and the limit from the right, we can see where we're headed. So we can use that to help us. So we already know the answer to the first one because we're using the same rational function from the last picture. We should get that it is negative 5 halves. And what we can see is that is indeed true because that's what I have highlighted on the graph. When we come from the left and the right, we are right at that hole. So that's why this function has removable discontinuity at 2, and we get a value of negative 5 over 2. So what if we look at 4? What you'll notice at 4 is, that's the other half. Let me just move up and show you the simplified fraction. That's the other factor that we could not remove. So what we notice at the graph is that we have a vertical asymptote. So how do we deal with that? What we do is we look at the limits from the right and the left and make a judgment for that. If they're the exact same value and it's a real value, we can find the limit at 4. If they are different or they are infinite, then the limit does not exist. So the first one is looking from the right and the second one is from the left. So coming from the right side of 4, we see that this function is definitely headed to positive infinity. And if we come from the left-hand side, the left-hand limit is headed to negative infinity. So technically there is no limit at 4, but the left and right-hand limits can be defined as negative infinity and in positive infinity respectively. Okay. All right, so please remember that if you get those undeterminate forms, your goal is to algebraically manipulate the expression to remove those points of discontinuity and then try direct substitution. So we're going to stop this video here, and then we are going to find some one-sided limits and move on from there.